Okay, fine. So in the previous class, we were discussing about uh, the basics of finite element analysis. So in today's class, let us try to have a brief understanding of the history of the development phases that gave rise to this technique called finite element analysis. So basically, what happened in the year 1941? These two people by the name Reencroft, what they did, they made use of a combination of something called as 1D elements, which we will be discussing in detail in order to solve problems regarding to stress analysis. Okay, this basically set for the beginning of finite element analysis. E phase in uh, the development of finite elements started. Okay, I will not be explaining these things in detail because uh, this is not so important given the. Okay, let me just yes it through. So in 1941, Reenkoff and McHenry, what they did, they made use of something called as 1D elements to solve problems on stress analysis. Then in the year 1943, this guy called Courant started making use of variational form. This is basically based on variational calculus that he has studied in probably mathematics 4. He made use of variational calculus and converted it into something called as piecewise interpolation. Again, we will be discussing this in detail. So then what happened in the year 1953, uh, this guy called Levy developed something called as stiffness or displacement method. So the problems that we will be solving, and the modern day finite element analysis is uh, totally dependent on this method. So this is the method that we will be following. So this guy called Levy, he developed stiffness or displacement method of finite element formulation. Then in the year 1954, Argyris and Kelsey, they developed matrix methods, right? They developed matrix methods using energy methods. So you know that you know the concept of strain energy. By making use of the concept of strain energy, they developed equations in the form of matrices to solve problems on structural analysis. Then, so till this phase, the problems that we will be solving, that were being solved, was only restricted to 1D elements. ಅಂದ್ರೆ ಏನೋ ಒನ್ ಡೈಮೆನ್ಷನಲ್ ಎಲಿಮೆಂಟ್ಸ್ ಮಾತ್ರ, ಅಂದ್ರೆ ಆರ್ ಒನ್ ಡೈಮೆನ್ಷನಲ್ ಪ್ರಾಬ್ಲಮ್ಸ್ ಮಾತ್ರ ದಿ ಟೆಕ್ನಿಕ್ ವಾಸ್ ರೆಸ್ಟ್ರಿಕ್ಟೆಡ್. ಇನ್ ದಿ ಇಯರ್ 1956, ಟರ್ನರ್ extended the formulation for two-dimensional analysis as well. So this happened in the year 1956. Then in the year 1960, this is again an important phase because in this year, this guy called Clow, he introduced the term finite element. He introduced the term finite element. Then in the year 1961, Melosh developed the stiffness matrix for bending elements. So till here, it was only restricted to axial forces. Now in the year 1961, it was extended to bending forces as well. Then in the year 1965, three with the name Clow, Rashid and Wilson, they developed something called as axisymmetric elements. This is again a benchmark phase. Axisymmetric elements ಅಂದ್ರೆ basically, if you can try to recall from your geometry, there are certain solids called as solids of revolution. ಹೌದಾ? So suppose if you take a right angle triangle and if you rotate it by 360 degrees about its axis, ಏನಾಗುತ್ತೆ? You will get a cone. ಹೌದಾ? So basically what is happening, ಯಾವುದೋ ಒಂದು ಬೇಸ್ ಶೇಪ್ ನ ತಗೊಂಡು ಯು ಆರ್ ರೊಟೇಟಿಂಗ್ ಇಟ್ ಬೈ 360 degrees. So basically what is happening, out of a plane you are generating a solid. So they are called as solids of revolution. ಅದೇ ಕಾನ್ಸೆಪ್ಟ್ ಮೇಲೆ ಬೇಸ್ ಆಗಿರುವಂತ ಆಕ್ಸಿಸಿಮೆಟ್ರಿಕ್ ಎಲಿಮೆಂಟ್ಸ್ ನ these three engineers they developed it. This was in the year 1965. Again in the same year, the concept of finite element formulation was extended to vibration analysis, that is dynamic analysis. So these two things happened in the year 1965. Then in the year 1969, Sabo and Lee, they developed something called as weighted residual formulation. Again, this is there in your syllabus in the first module itself. We will be discussing what is weighted residual formulation in detail in the coming classes. Then in the year 1970, this again marks an important phase. ಸೊ ಇಲ್ಲಿ ತನಕ ಏನಾಗ್ತಾ ಇತ್ತು, ನಾವು ಇನಿಷಿಯಲ್ ವ್ಯಾಲ್ಯೂ ಪ್ರಾಬ್ಲಮ್ಸ್ ಮತ್ತೆ ಬೌಂಡ್ರಿ ವ್ಯಾಲ್ಯೂ ಪ್ರಾಬ್ಲಮ್ಸ್ ಮಾತ್ರ ಸ್ಟಡಿ ಮಾಡ್ತಾ ಇದ್ವಿ. ಬಟ್ ಇನ್ ದಿ ಇಯರ್ 1970, transient state analysis kuno the concept was extended. This was done by two engineers by the name Zinkiewicz and Parek. This engineer, this guy Zinkiewicz, is known as he can be called as father of modern day finite element analysis. Again, he has authored a couple of books on finite element analysis, which are excellent books. So he is credited to be the father of modern day finite element analysis. Then in the year 1976, this Russian by the name Belichko, he extended the technique to nonlinear dynamics, that is for nonlinear vibrations. So these are the important phases through which finite element analysis was evolved. ಸೊ ಇಲ್ಲಿ ಬೇಸಿಕಲಿ ನೀವು ಏನ್ ಜ್ಞಾಪಕ ಇಟ್ಕೋಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ, ಯೂಶಲಿ there will be a question asking you to give a brief historical account of the finite element method. So probably ಇದನ್ನ ಒಂದು 6ರಿಂದ 10 ಮಾರ್ಕ್ಸ್ ತನಕ ಕೇಳ್ತಾರೆ. So if this question is asked, you just need to reproduce this table. This is ಏನಫ್. ಸೊ ನೀವು ಹಿಸ್ಟ್ರಿ ಅಂತ ಹೇಳಿದ್ರೆ ತುಂಬಾ ಇದನ್ನ ಜ್ಞಾಪಕ ಇಟ್ಕೊಳ್ಳೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ. ಸೊ ಇಂಪಾರ್ಟೆಂಟ್ ಫೇಸಸ್ ನಾನು ಏನೇನು ಹೈಲೈಟ್ ಮಾಡಿದ್ದೀನಿ, ದಟ್ ಇಸ್ ಸಫಿಶಿಯಂಟ್. ಯು ಜಸ್ಟ್ ನೀಡ್ ಟು ರಿಮೆಂಬರ್ ಇಟ್ ಅಂಡ್ ರೀಪ್ರೊಡ್ಯೂಸ್ ಇಟ್. ಸೊ ದಿಸ್ ಎವಾಲ್ವ್ಡ್ ಇನ್ ಎ ವೆರಿ ಲಾಜಿಕಲ್ ಮ್ಯಾನರ್. ಯಾಕೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಫಸ್ಟ್ 1D ಎಲಿಮೆಂಟ್ಸ್ ಇಂದ ಶುರುವಾಯಿತು, ಆಮೇಲೆ 2D ಎಲಿಮೆಂಟ್ಸ್ ಬಂತು. ಇಲ್ಲಿ ತನಕ ಆಕ್ಸಿಯಲ್ ಫೋರ್ಸಸ್ ಮಾತ್ರ ಇದ್ದಿದ್ದು, ನೆಕ್ಸ್ಟ್ ಬೆಂಡಿಂಗ್ ಫೋರ್ಸಸ್ ಡೆವಲಪ್ ಆಯಿತು, ಆಮೇಲೆ ಆಕ್ಸಿಸಿಮೆಟ್ರಿಕಲ್ ಎಲಿಮೆಂಟ್ಸ್ ಡೆವಲಪ್ ಮಾಡಿದ್ರು. ಇಲ್ಲಿ ತನಕ ಏನಾಗ್ತಿತ್ತು, ಬರೀ ಸ್ಟ್ಯಾಟಿಕ್ ಫೀಲ್ಡ್ ಪ್ರಾಬ್ಲಮ್ಸ್ ಮಾತ್ರ ಇತ್ತು. ಅದಾದ್ಮೇಲೆ ಇನ್ ದಿ ಇಯರ್ 1965 ಇಟ್ ವಾಸ್ ಎಕ್ಸ್ಟೆಂಡೆಡ್ ಟು ಡೈನಮಿಕ್ ಅನಾಲಿಸಿಸ್ ಲೈಕ್ ಫಿಟಿಗ್ ಲೋಡಿಂಗ್ ಅಂಡ್ ವೈಬ್ರೇಷನ್ಸ್. ದೆನ್ ಇನ್ ದಿ ಇಯರ್ 1969 weighted residual formulation ಬಂತು. ಅದಾದ್ಮೇಲೆ ಟ್ರಾನ್ಸಿಯಂಟ್ ಫೀಲ್ಡ್ ಪ್ರಾಬ್ಲಮ್ಸ್ ಬಂತು. ಅದಾದ್ಮೇಲೆ ನಾನ್ ಲೀನಿಯರ್ ಡೈನಮಿಕ್ಸ್ ಗೆ ದಿ phases were evolved. What is important to notice, all the persons that are mentioned in the slide, they are all basically mechanical engineers. So this is something which is of a great pride to mechanical engineers. ಬೇರೆ ಎಲ್ಲ ಕೇಸಲ್ಲಿ ಏನಾಗಿತ್ತು, essentially the science underlying the problems that we were studying were basically developed by physicists. ಹೌದಾ, ಫಿಸಿಸಿಸ್ಟ್ ಗಳು ಡೆವಲಪ್ ಮಾಡಿ ಅಥವಾ ಮ್ಯಾಥಮೆಟಿಷಿಯನ್ಸ್ ಡೆವಲಪ್ ಮಾಡಿ, then we made use of those techniques to develop technologies. But in this case, this entire field, finite element method, was developed by mechanical engineers, and later mathematicians made use of these techniques to solve their problems. So this is a groundbreaking innovation as far as mechanical engineering is concerned, because all the people who are responsible for the development of this technique were engineers, unlike the other techniques. Okay, you just need to remember this. You need not worry too much about this. So let us move on. Okay, now what you are seeing, let us now try to understand what do we mean by this word finite element, right? So illi the picture that you are seeing on your right, this is basically a hand prosthetic. This is basically a prosthetic arm of a weightlifter, right? So due to some reasons, his arm was amputated. Then since he was a professional weightlifter, the case was given to develop a prosthetic for him. So as you can see, probably this might be the lever of a bench press. So basically these projections are replicating the fingers of that wrestler or weightlifter. So this basically is the arm. So what is the problem associated with it? Suppose one of the most important thing that we need to consider while designing this artificial arm or the prosthetic is, what is the load bearing capacity, or what should be the load bearing capacity of this arm, right? So probably say Let us say that the weightlifter is capable of uh, lifting a force of say 100 kgs, sorry, 1000 kgs, right? So let us assume that this weightlifter is basically capable of lifting a load of 1000 kgs. So suppose if I am designing this prosthetic, the prosthetic should not get deformed or it should not fail upon taking up this load. This is one important thing that we need to consider while designing it. But at the same time, what is also to be remembered is, suppose if the load carrying capacity of this body increases, and if the weightlifter is capable of carrying a much greater weight, it means to say that to carry a greater weight, I need to increase the dimensions. Suppose for a given case, if I increase the force, then it automatically translates that I should increase the dimensions of the prosthetic as well. Now, what happens if I increase the dimensions of this component? Increase in dimension will result in increase in weight of the arm, right? Increase in the dimensions will result in increase in the shape of the arm. Now, what does this mean? It means to say that whenever this artificial arm or the prosthetic is fitted into the hand of that person, he need to bear a greater amount of dead weight. This basically is a dead weight. So what will happen because of this dead weight? He will feel fatigued because
Hello.
because of this he need to constantly carry the weight of the prosthetic. So thereby he will get fatigued. Now, as a result of which, what needs to be done? We should minimize this dead weight as far as possible. Now, how can we minimize this dead weight? The first thing is we can make use of different materials. We can make use of materials that are having lower density. So, lower density means the weight involved will be less. This is one thing that can be done. Second important consideration that we need to make use of is the material that we will be chosen. The material that we will be choosing should be biocompatible. It means to say that it should be compatible with the tissues of the body. It should not be a toxic material such that it will react. It should not react, and it should not cause any biological problems. So as a result of which, the options that we are having is very limited. And again, we cannot significantly modify the design because this is basically developed to carry weight or to lift the weight, as a result of which we cannot really tinker around with the shape of this component as well. So ಹಾಗಾಗಿ ಏನ್ ಮಾಡ್ತೀವಿ, the options that are available is very limited. So what is that we need to do? Once we have chosen the material and once we have designed, we should think about something called as optimization. What is optimization? What is optimization? Suppose in the previous semester we have solved problems on design of machine elements. So ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತಾ ಇದ್ವಿ ನಾವು ಅಂತ ಹೇಳಿದ್ರೆ, ಯಾವುದೋ ಒಂದು ಕಾಂಪೊನೆಂಟ್ ನ ಡಿಸೈನ್ ಮಾಡಬೇಕಾದ್ರೆ we were making use of something called as factor of safety. Factor of safety was extensively made use of. This value of factor of safety ranged all the way from 2 to sometimes 4. Factor of safety, the value of factor of safety ranged from 2 to 4. Now, basically, what will happen? What do we mean if the factor of safety is 2? Suppose if I am designing this body to carry a load of 1000 kgs, and if I am making use of a factor of safety of 2, what is that I am essentially doing? I am designing the body to take care of this into 2 times. ಅಂದ್ರೆ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿನ ಇಟ್ ಇಸ್ ಅ ಮಲ್ಟಿಪ್ಲೈಯರ್. ಸೊ ನಾನು 1000 kgs ಸಸ್ಟೈನ್ ಮಾಡೋದಕ್ಕೆ ಒಂದು ಬಾಡಿ ಡಿಸೈನ್ ಮಾಡಿ, ಇಫ್ ಐ ಆಮ್ ಮೇಕಿಂಗ್ ಯೂಸ್ ಆಫ್ ಎ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಆಫ್ 2, ಎಸೆನ್ಷಿಯಲಿ ಐ ಆಮ್ ಡಿಸೈನಿಂಗ್ ದಟ್ ಬಾಡಿ ಟು ಕ್ಯಾರಿ 2000 kgs. ಅಂದ್ರೆ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಇಂಟು ರೇಟೆಡ್ ಲೋಡ್. ದಿಸ್ ಇಸ್ ವಾಟ್ ದಿ ಕಾನ್ಸೆಪ್ಟ್ ಇಸ್. ಬಟ್ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, by making use of a factor of safety of 2, it will increase the dead weight of the prosthetic by 2 times. Suppose the artificial arm, suppose if the weight of this arm is say around 100 grams, ನಾನು ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ 2 ಯೂಸ್ ಮಾಡ್ಬಿಟ್ರೆ ದಿ ವೇಟ್ ಆಫ್ ದಿಸ್ ಆರ್ಮ್ ವಿಲ್ ಬಿ 200 grams. Essentially, the dead load will also be doubled. So what is that we need to do? We need to make sure that the factor of safety is almost equal to 1. This is what we call optimizing. So optimization ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀವಿ, we will uh, we will judiciously and we will intelligently design a component such that it will not fail under any operating conditions, and still the factor of safety is almost equal to 1. Again, 100% 1 use ಮಾಡೋದು ಕಷ್ಟ. It may be somewhere around 1.1, or it might somewhere even be around 1.01. So what is the advantage of doing this? The advantage is the dead weight of the body will be reduced. So this is one advantage. So in order to optimize this, we will resort to this finite element method. So basically what you are seeing on the left, is the finite element model of the prosthetic that was developed. So you can now see each there are this model is composed of tetrahedrons, as I am highlighting here. So there are multiple number of tetrahedrons. So this prosthetic is divided into multiple number of elements. So each triangle or each tetrahedron that is present here, it is basically a three-dimensional body, is called as an element. Now each element is having a finite shape. Each element is having a finite shape as well as finite size. So a given single body is divided into multiple number of elements. But what is that you need to remember? You need to remember that each element is finite in shape as well as finite in size, and the number of elements that are present is also finite. Andre say if you are dividing this body into 1000 elements, ಎಷ್ಟು ಎಲಿಮೆಂಟ್ ಆಗಿ ಡಿವೈಡ್ ಮಾಡಿದೀವಿ ಅನ್ನೋದು ಇಟ್ ಇಸ್ ಕೌಂಟಬಲ್, ಇಟ್ ಇಸ್ ನಾಟ್ ಇನ್ಫೈನೈಟ್. So the number of elements is finite. Each element is having a finite shape and a finite size. Let us look at another example. Now basically this is more or less the we call it as wireframe model. Of a fighter jet. This is almost similar to the Dassault Rafale that was procured in the previous year. So basically, you can see the body of the entire aircraft. This body is basically divided into multiple number of elements which are having different shapes and different sizes. So if you can see here, in these cases the elements are triangular in shape, but here the elements are rectangular in shape. Here again the elements are triangular. Here the elements are cylindrical. So essentially this entire body is divided into multiple number of elements which are having different shapes and different sizes. But still we know the shape of the element, we know the shape of each element, we know the size of each element, as well as the total number of elements in the entire model. The total number of elements in the entire model is completely known. Okay, so the shape as well as size and the number of elements is completely known. That is what we need to remember. Okay, fine. Now essentially what we are trying to do, if we consider the example of this aircraft, what is the objective? The objective is again to optimize this. Now what do we mean by optimization? Why is it necessary? So you have studied about composite materials. So essentially probably this case study would have been told to you by by the faculty who has taught you this composite materials. So basically, composite materials are extensively used in manufacturing of aircrafts. Now, why is the use of composite materials advocated? Composite materials na ಯಾಕೆ ಯೂಸ್ ಮಾಡ್ತೀವಿ? It is made use of because its strength to weight ratio. Strength to weight ratio is higher. ಅಂದ್ರೆ essentially how we measure strength. Strength is measured in terms of Young's modulus in most of the cases. In some cases, it is even measured in terms of yield strength or ultimate strength based on the type of the material. So this value, let us say yield strength of the material divided by the weight of the material for that particular strength, it is extremely high in case of composite materials. Yake, there we will be making use of a matrix phase and a reinforcement phase. Basically, ಅಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ, essentially the objective is to reduce weight. Now, why should we reduce weight? You might have heard about this case study. ನಿಮ್ಗೆ ಏರ್ ಇಂಡಿಯಾದಲ್ಲಿ ಅಥವಾ in most of the cases, what we say, in most of the airlines, they only hire air hostess. They do not prefer stewards.
ಗೋಯರಲ್ಲಿ
ಸುಮಾರು ಯಾವ್ದೋ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಏರ್ಲೈನ್ಸ್ ಅಂತ ಏನಲ್ಲ, ಆಲ್ಮೋಸ್ಟ್ ಎಲ್ಲಾ ಏರ್ಲೈನ್ಸ್ ಅಲ್ಲೂ ಇದೇ ಪ್ರಿನ್ಸಿಪಲ್ ನ ಫಾಲೋ ಮಾಡ್ತಾರೆ. ಎಸೆನ್ಷಿಯಲಿ ದಿಸ್ ವಾಸ್ ಪ್ರಾಬಬ್ಲಿ ಸ್ಟಾರ್ಟೆಡ್ ಬೈ ಏರ್ ಇಂಡಿಯಾ. ಯೂಶಲಿ ನಿಮ್ಗೆ ಮೇಲ್ ಕೌಂಟರ್ ಪಾರ್ಟ್ಸ್ ನ ಹೈರ್ ಮಾಡಲ್ಲ. ದೇ ಆಲ್ವೇಸ್ ಪ್ರಿಫರ್ ವಿಮೆನ್. why is it so? The reason is because the average weight of a woman is always less when compared to the average weight of a man. Probably the average weight of a woman may be somewhere around 50-55 kgs. Now, Indian women, when speaking of Indian women, but if we consider the average weight of Indian men, it may be somewhere around 70-75 kgs, or it might even go up to 80. Howda? So what does this mean? This means that if you hire a female uh, a female attendant, basically the load that the aeroplane is supposed to carry, the load that the flight is supposed to carry, is approximately reduced by 30 kgs. Is approximately reduced by 30 kgs. So this translates to savings in a lot of fuel. Fuel cost ಅಂತಂದ್ರೆ ಏನು, because each and every kg of weight that is added will consume more number of fuel because a greater mass is supposed to be transported. ಹೌದಾ? That is the weight in an aircraft. That is the importance of weight in an aircraft. You might have even heard about a different case study. Probably, I don't know if probably it may be from Lufthansa Airlines, this German airlines. ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತಾರೆ ಅಂತ ಹೇಳಿದ್ರೆ, when they were serving meals to their passengers, there were those people from Europe, they will extensively make use of olives. Olives, we can imagine it will be of the same size of, say, ಪ್ರಾಬಬ್ಲಿ ಸ್ಮಾಲ್ ಲೆಮನ್. ಹೌದಾ? ಅಥವಾ ಇನ್ನೂ ಚಿಕ್ಕದಾಗಿರುತ್ತೆ ಆಲಿವ್ಸ್. ಸೊ ವಾಟ್ ದೇ ಡಿಡ್, ಅವರ ಪ್ಯಾಸೆಂಜರ್ಸ್ಗೆ ಮೀಲ್ ಸರ್ವ್ ಮಾಡಬೇಕಾದ್ರೆ, ಇನ್ ಒನ್ ಕೇಸ್ ಸ್ಟಡಿ, ದೇ ರಿಮೂವ್ಡ್ ಒನ್ ಆಯಿಲ್ ಫ್ರಮ್ ಈಚ್ ಪ್ಲೇಟ್ ಆಫ್ ಮೀಲ್ ದಟ್ ವಾಸ್ ಬೀಂಗ್ ಸರ್ವ್ಡ್. ಸೊ ಎ ಸಿಂಪಲ್ ಆಲಿವ್, ಪ್ರಾಬಬ್ಲಿ ಆಲಿವ್ ಸೈಜ್ ಏನಿರುತ್ತೆ ಆಲ್ಮೋಸ್ಟ್ ನಮ್ದು ಬೆಟ್ಟದ ನೆಲ್ಲಿಕಾಯಿ ಸೈಜ್ ಅಲ್ಲಿ ಇರುತ್ತೆ. ಇಟ್ ವಿಲ್ ಬಿ ಇನ್ ದಿ ಸೈಜ್ ಆಫ್ ದಟ್ amla. So basically, by just removing a single olive from each plate, they were able to save crores of rupees in fuel costs. So that is the importance of saving weight in the aircraft. So ಆ ಕೇಸಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀವಿ, in order to optimize the weight of the aircraft, optimize the weight of the aircraft, we will extensively make use of finite element analysis. How ಇದನ್ನ ಹೇಗ್ ಮಾಡ್ತೀವಿ ಅನ್ನೋದನ್ನ we will try to understand it in the coming slides. ಸೊ ಇಲ್ಲಿ ನಾವು ಎಸೆನ್ಷಿಯಲಿ ಏನ್ ಮಾಡಿದೀವಿ, ಏರ್ಕ್ರಾಫ್ಟ್ ದ ಬಾಡಿನ ತಗೊಂಡು, ಬೈ ಕನ್ಸಿಡರಿಂಗ್ ದಿ ಏರ್ಕ್ರಾಫ್ಟ್ ಆಫ್ ದಿ ಬಾಡಿ, ಐ ಆಮ್ ಡಿವೈಡಿಂಗ್ ದಟ್ ಬಾಡಿ ಇಂಟು ಮಲ್ಟಿಪಲ್ ನಂಬರ್ ಆಫ್ ಎಲಿಮೆಂಟ್ಸ್. Right? I am dividing this body into multiple number of elements. In doing so, I am having a greater deal of flexibility in choosing the element as well as size of the element. ಹೌದಾ? ಸೊ ಹೌ ಇಸ್ ಇಟ್ ಅಚೀವ್ಡ್? ಬೇಸಿಕಲಿ ಇಲ್ಲಿ ನೋಡಿದ್ರೆ, ದಿಸ್ ಇಸ್ ಒನ್ ವಿಂಗ್ ಆಫ್ ದಿಸ್ ಏರ್ಕ್ರಾಫ್ಟ್. ವಾಟ್ ಐ ಕ್ಯಾನ್ ಡೂ, ಐ ಕ್ಯಾನ್ ಕನ್ಸಿಡರ್ ದಿಸ್ ಎಂಟೈರ್ ವಿಂಗ್ ಆಫ್ ದಿ ಏರ್ಕ್ರಾಫ್ಟ್ ಟು ಬಿ ಎ ಟ್ರಪೀಸಿಯಂ. I can model it using a single element. ಹೌದಾ? Essentially, I could have done this. But instead, what is that I am doing? I am making use of multiple number of elements. But I am making use of multiple number of elements. So this process of dividing a continuous body, the process of dividing this continuous body into smaller number of elements, process of dividing a continuous body into smaller number of connected elements is called as discretization. It is called as discretization, or in simpler terms, it is also known as meshing. It is also known as meshing. So what is the model that you are seeing here is called as wire frame mesh of the aircraft. ಸೊ ಈ ಮೆಶ್ ಅನ್ನೋ ಪದನ ಯಾಕೆ ಉಪಯೋಗಿಸ್ತಾ ಇದೀವಿ? ಯು ನೋ ದಟ್ ಮೆಶ್ ಅಂತಂದ್ರೇನು? ಇಟ್ ಇಸ್ ಎಸೆನ್ಶಿಯಲಿ ಸಾರ್ಟ್ ಆಫ್ ಎ ಸ್ಲೀವ್, ಸಾರ್ಟ್ ಆಫ್ ಎ ಸೀವ್. ಹೌದಾ? ಸೊ ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತಾ ಇದೀವಿ? We are having a similar structure here. That's why this process is called as meshing, and the generated model is called as meshed model or simply a mesh. So ಇಲ್ಲಿ ನೋಡಿ, in this figure you can see there is this wing of an aircraft. There is this wing of an aircraft. Now I am dividing this body, which is continuous in nature, into multiple number of elements. So ಇಲ್ಲಿ ಯಾವುದೋ ಒಂದು oddly shaped wing ಇದೆ. I am making use of square elements in order to model it. This process is called as discretization or meshing. So ಇಲ್ಲಿ ಏನಾಗಿದೆ, in the left hand side, in the figure that you are seeing on your left, I am making use of large sized elements. Squares are relatively larger in size. The squares are relatively larger in size. Thereby, the number of squares present is less. ಸೊ ಪ್ರಾಬಬಿಲಿ ಇಲ್ಲೊಂದು 20 ಸ್ಕ್ವೇರ್ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಬಲಗಡೆ ನಿಮಗೆ ಪ್ರಾಬಬಿಲಿ ಒಂದು 60-80 ಸ್ಕ್ವೇರ್ ಇರ್ಬೋದು. ದಿ ನಂಬರ್ಸ್ ಆರ್ ನಾಟ್ ಎಕ್ಸಾಕ್ಟ್. ಸೊ ಎಡಗಡೆ ಏನಾಗಿದೆ, ಆನ್ ದಿ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್, ದಿ ಮಾಡೆಲ್ ಇನ್ ದಿ ಲೆಫ್ಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ಕನ್ಸಿಸ್ಟ್ಸ್ ಆಫ್ larger elements. The size of the element is large, whereas the number of elements is small. ಹೌದಾ? Here, so there are two parameters: size of the element, number of elements. So in this particular model, the size is large, the number is small. The size is large, the number is small. So in the right hand side, the size of the elements is small, whereas the number of elements is large. So this case, where the size is greater, this type of mesh is called as coarse mesh. If the model consists of finer sized elements, and then if the model consists of small sized elements, then it is called as fine mesh. Then it is called as fine mesh. So difference between coarse mesh to fine mesh ಅರ್ಥ ಆಗಿದೆಯಾ? Is the concept clear?
Yes, sir.
Okay, fine.
Sir, previously